Okay, so for our second talk, or in this session, Sam Raskin will be giving the first of his series of lectures on geometric Langlands and 3D mirror symmetry.
Thank you so much for having me. I know it's late for many of you, and maybe even more obscure hours for some of you, and so I really appreciate everyone coming to hear me talk about this stuff. So this is the first in 3 talks about geometric Langlands and 3D mirror symmetry. I want to say that this is all joint with Justin Hilburn. That's kind of not so readable. Okay. With that, I'm going to turn the screen sharing off and just sort of ask you all to excuse my indulgence for a little bit while I tell a story about this this work. So first of all, I swore we were going to get the paper online before this talk. This was my deadline, and I missed the deadline. So so it goes. I'm really hoping that tomorrow it'll be online, but we'll have to see. I think definitely by the end of my talks. Oh, please. So so that's the first thing, and so apologies that it's not available yet. But the second thing I wanted to say is I just sort of wanted to describe a little bit. I wanted to ask you all to just indulge my maybe story about myself and my relationship to this work. So in the course of working on this project with Justin, I sort of, well, I guess I should say, like, I really, maybe more than a lot of mathematicians, didn't get a good education in physics as a young person. I think the last time I took a class was in high school. And there were many like English requirements when I was in college. And so I didn't have so much space in my schedule for physics classes. And so I'm kind of very ignorant. I'm still learning the grammar. And so if I conjugate verbs wrong or something, I please excuse me and correct me and everything. So I started grad school, in like working on stuff in algebraic geometry and representation theory, and especially geometric Langlands program kinds of things. And at the time, this like Kapustin-Witten thing was in the air. It was a kind of as a physical interpretation of what was happening in geometric Langlands. And for myself, that seemed like something super cool. I also didn't understand it at all at the time, but I kind of tried to ask around. Like, well, there were some things that seemed like a little bit off, like on the spectral side, it seemed to treat like basically Riemann surfaces as if they were just sort of topological manifolds, and that's sort of not the way that geometric Langlands works. And and there were other things that seemed weird. So I asked around a little bit, like if it had new ideas about how to kind of solve problems in the area or something, and no one seemed to think that, if all you were interested in was like geometric Langlands, that you were going to find something like new problem solving ideas there or something. It was more like interpreting it in the physical language. And so I didn't pursue it a ton at the time. And, whatever, I was a young grad student and didn't always know, what things to study or not to study. And so, but that was sort of where it stood for me at the time, was like, it seemed like that it was bringing the mathematics that existed into the framework of the physicists, but that there wasn't, I didn't see where there would be sort of motion in the other direction. And a little bit what I want to tell is the story of like how that kind of happened, and sort of say some, and eventually describe some kind of real conclusions about this stuff. So, and theorems. And and so it kind of, so basically what I have since sort of come to learn is that geometric Langlands in the physics language, apologies for everyone who knows this stuff super well and better than me, is a basically twisted form of S-duality for four-dimensional Yang-Mills theory. And so, like, roughly speaking, like, you have this kind of duality. It says that two quantum field theories are supposed to be the same. So for me, as a mathematician, it's a conjecture. It's a conjecture people believe and know how to probe, but it's not something that I think physicists claim to know how to sort of rigorously prove or anything. And this particular duality by itself, maybe if all you do is look at it in isolation, you don't see anything new. But you can consider its relationship with other dualities that exist in physics. And some of these dualities still don't have mathematical counterparts. And some of them have mathematical counterparts that were sort of developed only later. And so the work I'm going to describe is sort of making rigorous some particular conjecture in that framework of taking other physical duality conjectures that are sort of surrounding the, what I think of as geometric Langlands, and turning that into some kind of, concrete mathematics. And for me, it's super exciting. Kind of the geometry that's involved is stuff that seems hard and fun to me. Sort of algebraic geometry of loop spaces and things like this that I spent a while thinking about many years ago. And it's fun to have something kind of new to think about it. And in some ways, this problem is one I thought about even as a grad student and didn't know the answer to. And it's fun to see where it comes from. So maybe I'll just say as one other kind of thing, one of my kind of major things that I took away from this is that the real robustness of physics comes from like of this, like for the mathematician, like what are we missing? Basically, like all of these dualities, they're sort of they're packaged up into I don't know. Maybe the biggest thing is string theory dualities and M theory and things like this. And it's kind of totally inaccessible, it seems, to physicists. It's totally inaccessible to mathematicians. And yet there's this sort of like furtive glance of something that's going on there, and that you can sort of pull out of it like real kind of mathematical things. And right now we don't, that exists only in this like fuzzy state in the physics literature, and in math we don't have anything nearly so powerful. And all we have are sort of like, you kind of run the machine, and then you at the sort of last step try to turn that into mathematics, but we don't have a way of turning the first step into mathematics, at a level that would, I mean, again, there are things you can do, but at a satisfactory level yet, or completely satisfactory level. And so, yeah, so that's kind of the stuff I want to describe. In some ways, I have to warn that this series of talks, it might be a little bit aimed at myself 2 years ago or something like that. So I'm going to try to, I'd say people should ask questions, and I'll do a better job if people ask more questions. And I want to try not to take for granted certain bits of jargon, but it might just kind of happen because when it's a story about things I learned or something, it's not going to. I'll have a tendency, I think, to take for granted the things I knew before at the beginning of the story. So with that, let's get started. So this is joint with Justin Hilburn, and sort of maybe for physicists, let me just sort of say just very briefly what the upshot of the story is. So we compare line operators in like an A-twisted pure hypermultiplet theory, 3D theory, and B-twisted U1 gauged hypermultiplet. So I should in particular say everything is abelian in our work, and sort of moreover, we consider these as boundary theories for kind of twisted U1 gauge theory, where kind of on one side it's an A twist, on the other side it's a B twist, and those two twists are exchanged by electromagnetic duality. So those are some orienting words. It'll be a while until we actually get there. So it's just some kind of a little bit maybe orienting. And this is supposed to be, I should say, kind of the, in some sense, simplest example of 3D mirror symmetry that has certain kind of, well, simplest example of line operators for 3D mirror symmetry in a way that is kind of has certain bad features or difficult features. So, okay, so now I sort of want to get started on mathematicians. So I want to start with just a kind of question, which is like, what I want to talk about right now. So what I want to discuss is some kind of like basically algebraic geometry. So stuff that kind of works over fields of characteristic zero, for instance, not necessarily the complex numbers. So I want to not allow myself the tools of complex geometry. Of course, we can appeal to them as analogy, but I want statements that exist in this framework. And this is going to be of sort of three-dimensional quantum field theories. So as you can see, there's a 3D hidden away up here. And so, and on the other hand, I'm an algebraic geometer, so I sort of want to be able to combine these two things. And so a long time ago, I learned that curves are like two-dimensional things. So things living on curves are two-dimensional. And so what should it mean? So basically like, what does this like possibly mean? And so I just sort of want to give a kind of quick answer. So when I say, what does this mean? Like, well, 2D, it wouldn't be a surprise because curves are analogous to complex like curves, and those have two real dimensions. So what should a 3D theory mean? So I just sort of want to give a quick definition. So, so first of all, just a reminder, everyone knows. A three-dimensional topological field theory assigns so a number. So this is, I should say, a fully extended. So I'll write 0, 3 extended. Assigns a number to a 3-manifold, a vector space to a 2-manifold, a category, so to a 1-manifold, and 2 category to a 0-manifold. So this is like, you know, this Atiyah's interpretation of topological field theory. In the extended form, it's due to probably Baez Dolan and Hopkins and Lurie, and really got, I think, advertised a lot after Lurie's work on the cobortism hypothesis. And this is the sort of, you know, these are the words you're supposed to say. Let me highlight that in practice, these things tend to be kind of derived objects. So even theories coming out of physics, vector spaces might really be chain complexes of vector spaces. Categories might really be DG categories and this kind of thing. So a DG category means something enriched over chain complexes of vector spaces, not mirror vector spaces. So there's a kind of algebraic version of this that we can make sense of. So I don't know what a 3-manifold is, and I don't know what well, I do know what a 0-manifold is, but I fail in examples to make sense of this. Well, okay, how should I organize these ideas? So So the first thing is that this is like this kind of topological field theory. It's a little bit defined on all. It is defined on all manifolds, and sometimes that's not the way you should think about field theories. Sometimes you're supposed to think about them living on a certain manifold. So the kind of bread and butter of physics is kind of some systems of differential equations for maybe sections of vector bundles, this kind of thing, on manifolds, and those can make sense for a single manifold in isolation. And this sort of formalism, it's kind of not as well worked out, but you could imagine doing this. You could imagine living in an ambient 3 manifold, and then for embedded 2 manifolds, you would attach a vector space, and for embedded 1 manifold, you would attach a category. And that's a little bit more the picture I want to have. And so now I want to say what sort of an algebraic 1-2 extended field theory is. So this is on curve X. So this is, I should say, it's a smooth and projective curve. So it is kind of an assignment of every time, well, first of all, my curve X, so maybe I'll call this theory T. So my curve X is going to map to some complex of vector spaces. So I treat my curve as if it's a 2 manifold, and this is going to get, therefore, a vector space assigned to it. You should sort of imagine all of this, by the way, taking place in some kind of like X times R is maybe the right way to think about it. And the theory is going to be sort of topological in that R direction. So if you're a physicist, that's probably a better way to be thinking about things. And then every time I have a point X and X, I can attach to this the punctured disk based at this point. So this is some kind of formal algebra geometric object, which is like you take the formal completion around this point and you remove the point. And this I'm going to imagine is a 1 manifold. So I treat it as being like a circle. And so this is going to give rise to some DG category, which is what the theory attaches to this, again, sort of circle you imagine based at the point. Now, given this, only some cobortisms are allowed. So in the usual kind of framework of topological field theory, kind of like everything is very symmetric, everything is very dualizable, and so on. And that's not the case for examples in the algebraic framework. So let me just sort of draw a picture real quick. So so I can form kind of the formal disk based at this point. I guess I won't write a hat. So this D sub X is kind of what I'm trying to draw in this picture. And I can think about this as a cobortism from the empty set into the punctured disk based at this point. So I think about it as a cobortism going in this direction. And so this cobortism is allowed. The one going the opposite direction, not allowed. I don't have a good explanation for this. It's just kind of the way things are. It's, you know, it's just an experimental fact for me. So this, yeah, so this gives rise to a functor from T of the empty set. So by definition, this is going to be kind of just the category of vector spaces. So it's some DG category. And for the empty set, it has to be sort of the unit one, which is vector spaces itself, to T of the punctured disk. And so this amounts to an object that I'm going to call the vacuum object at this point. Just there's some one-dimensional favored vector space in here, and everything's determined by where it goes. So this is kind of main cobortism 1, and main cobortism 2 is going to be that I can draw can I draw? Okay. So, so in this picture, I'm kind of drawing my curve minus the point, and I'm trying it big. It's bigger than just minus the point because the limits of. Okay, and so over here is, oh shoot, I did it the wrong way. Oh my God, I just did it again, the exact same wrong way. Sorry, everyone. Sorry, so 2 is going to be, okay, this time it really goes on the left-hand side. And so on top, this is a picture of x minus the point. This is a punctured disk over here to the left. And this is going to be the empty set over on the right. And this, again, I regard as a cobortism from the punctured disk to the empty set. And so this is going to give rise to a functor from this category that the theory attaches to a punctured disk to T of the empty set, which again is vector spaces. And this, roughly speaking, is supposed to be, so just to give this sort of a name, so it's this, maybe this name is a little bit fraught, but I'm just going to stick with it as something. I'm going to call this chiral homology for the theory T. And just, you know, things should sort of compose the way you expect. So so there's kind of small, I would say that this is like the working person's structure that's available to you here, but there's various other things that you should keep in mind. So you can sort of vary the point x, and things should work well in families as you vary this point. Also, there should be this sort of factorization condition, which if you know that, that's great. It's some kind of version. So like what a physicist, a mathematically minded physicist might say is that this category should be braided monoidal. In practice, it's not braided monoidal. And that's kind of too bad, but there's this stand-in people have instead called factorization categories or chiral categories. And it's some much weaker thing that you can imagine as a kind of like much weaker algebra geometric analog of a braiding. And it's more technically involved and so on, but it's the same kind of, if you think in terms of little disk operades and things like this, it's kind of very similar. Yeah, and so of course there should be other sort of axioms. So for example, if I kind of take this chiral homology, maybe I'll write it as kind of chiral homology. So if I apply this to the vacuum object at x, this is going to be like what the theory, this is going to be, so this is a functor from this category to vector spaces. I also have this favorite object here. And if I take this favorite object that's roughly composing these two cobortisms, and so you should get what the theory attaches to x. And there's some, you know, some dependence on the point a priori in this formula, but in fact, it's independent. So, okay, just, oh, and maybe I should add like these, yes, okay, so I see Jacques' question here. So if x were P1, then this does look like the same picture I drew, but in fact, it's not for me. So there's, although I would draw the same picture, and they're sort of, in some sense, topologically the same, there's a big difference in this algebraic setting about the formal disk on the one hand, which is what is appearing on top here, and A1, which is what's appearing over here. So maybe they're both kind of topologically the same, but in some sense they're not, you know, conformally the same or something, would be the differential geometry way of saying it. Yeah, and I have no ability to draw that in pictures. It's just Okay, what was I trying to say? Oh, I wanted to say that that really the fact that like these axioms are a good theory of like 1-2 extended field theories, that was something I really only appreciated from comments from my colleague David Bensby. Okay, so other questions, comments?
Sam, actually, maybe rather than trying to type it, this feels a little bit like some version of Siegel's axioms for 2D conformal field theory. That's to say, you really are, there really is sort of, in defining this formal disk, you're really picking a local conformal structure. Is that, am I totally off base there?
No. So I think the right thing to think here is that this is describing physical theories that are like kind of 3D physical theories that are holomorphic in 2 directions and topological in 1 direction.
I see, right. So, but really on this Riemann surface, we're sort of, these act like conformal field theories. They're holomorphic in the capital X direction.
Absolutely, yeah. Yep.
That's why these axioms sort of look a little bit more like Siegel than like Atiyah.
That's right, and it's also about this sort of universality in some ways that that I was trying to say before, like like in the usual Atiyah framework, it's not possible to just like modify a theory along some submanifold to consider some kind of like defect, basically, and because it has to be defined for all manifolds, so you can't do it along just like some submanifold. And this framework also is sort of taking into account that, like this category you attach to a puncture disk, it might be sort of the same for all puncture disks, or it might not be the same. For us, it'll always be it'll be kind of universal, but it's just worth keeping in mind in some way in the picture, I think.
Thanks.
Okay, so I want to give some kind of examples real quick for these things. So the first one, it takes some technical knowledge that maybe isn't universally held by everyone, but I think a lot of people know in some form. And it's great having Emily as the only person whose video is on, because she's definitely one of the people who knows this stuff, and so it makes me feel more comfortable doing it. So if A is, so this is kind of a big class of examples due to Valence and Indranil. So if A is chiral algebra, so this goes under other names, factorization algebra on X, and so this is a theory due to Valence and Drinfeld. So I'm saying due to, like, this is, well, the definition and all of the properties I'll say are due to them. And let me just add as more words that this is a sort of kind of, I should say, it's like it's a local on a general curve X analog of vertex algebra. So basically, one of these things that you can define on any curve, it's going to be some flavor of vertex algebra. So this is going to give rise to a 3D theory that I'll call, let's say, T sub A. And so, okay, so this is, every time I say this, people get upset, and so, because everyone wants it to be a 2D theory. So let's hold off on that for just a moment, and I'll get back to it in a moment. So what does this 2D theory look like? So if I take this theory and I evaluate it on a punctured disk at a point, this is going to be the category of modules for this vertex algebra supported at a point. So this is some definition. Again, it has all the sort of properties you need. It varies well. It has this sort of chirality property, this factorization property. And then this vacuum object in here is the, so to say, so-called vacuum representation of A, which is just the fiber of A itself at this point. And this functor, this chiral homology functor from A mod X to vect is what Valence and Indranil call, believe it or not, chiral homology. Okay, so this is so again, I want to acknowledge this annoyance that I've produced a 3D theory from something that looks like a 2D conformal kind of input data. And so first of all, I just want to say, look, you can see it with your eyes. You were convinced that this should be something like an algebraic version of a 3D theory, and here we go. That's the data we get over here. So I can't be to blame for it. The numbers add up this way, but also this is something kind of already familiar, maybe in some ways from just usual quantum mechanics or something like that. So basically, in quantum mechanics, you probably have some kind of associative algebra of observables and something like Hilbert space. And so let's just start with this algebra and not worry about the Hilbert space. So sort of the deformation quantization and not the like geometric quantization. So in this case, like there is a 2D topological field theory around. It attaches the category of A modules to a point, like modules over this observables to a point. That's a 2D topological theory that has the Hilbert space as like a boundary. So so this is kind of a little bit the way quantization works, is if you have something in n dimensions, like your favorite kind of n dimensional field theory, there's really going to be a sort of like n+1 dimensional theory that you get by deformation quantization, and an n dimensional theory that you get by geometric quantization. And the n dimensional theory is at the boundary of the n+1 dimensional theory. So yeah, so yeah, so this is also the comment everyone makes, and let me, it's sort of, it's something I want to say less deep than that kind of phenomenon. But like it's just like anytime you have this like algebra of like local operators in an n-dimensional setting, and you start thinking like, what do you get from that? It's really has the shape, if you think in Atiyah kind of terms, it has, or Siegel kinds of terms, it has the shape of really a kind of n+1 dimensional theory. And it's just the fact of life. And it's not something, well, okay. I don't want to comment too strongly about the relationship there. Okay, so this is A one of the vertex algebra studied by Castello-Gaiotto. So eventually A will be one of the, yes, I mean, sometimes this A will be one of the vertex algebra studied by Castello-Gaiotto, and sometimes they introduce other VOAs. Really, this is the same kind of circle of ideas, but sometimes their VOAs are not, they're lossy in some sense. Specifically on the A-twisted side, the VOAs they consider are like A plus great, and on the B side, the VOAs they consider, and they sort of acknowledge this, that they're lossy. Okay, so I want to give kind of two other examples because maybe not everyone knows chiral algebras and stuff like this, and so I just sort of want to make some kind of extra notation. So let's say that, so I'm going to give two other things that sort of look like the same, well, that look like different examples, and I'll say some words that like really they're kind of absorbed into this. So say I'm given some kind of, we'll call it like a target stack that I'll call script X. And I'm sorry, this is just a little bit, I want to keep the same notation as the paper. Or maybe I'll say Y. So then there is so a 3D theory that, for instance, assigns the category of D modules on the loop space, the algebraic loop space of Y. So this is some DG category to a puncture disk. So here, let's say like, so for example, if Y is equal to A1, then this loop space on Y, and I should say maybe these loops are kind of based at the point, which we can kind of ignore. So this loop space for Y is going to equal the sort of doubly, this like huge int pro infinite dimensional affine space of sort of canonically parametrizing Laurent series. So in other words, I imagine I have some affine space and it has some coordinates, and these, and like basically the coordinates are supposed to match to be like, so I have some, maybe I should say infinite dimensional manifold, and it has some basically canonical coordinates up to like some mild choices. And so like these canonical coordinates are like taking Laurent coefficients. And the flavor of that, like Laurent series are asymmetrical objects, right? Like you imagine them going off in both directions, but to the left they cut off. And that refers to the fact that this is some ind thing. It's kind of, Laurent series are union where you bound the order of pole. And then there's this pro thing that refers to the fact that sort of going to the right, you have infinitely many Laurent coefficients. And so this is some kind of, you take a product of infinitely many affine spaces, and then you start taking a union under shifts. And that's the kind of thing that it looks like. T star Y is going to be what's really considered. It'll be a sigma model into T star Y in this case. Yeah, thanks for the question. Yeah, and I also wanted to acknowledge that, like, yeah, Matt's giving a series of talks about related material, and that that's a great place to go for like a much better physical understanding of the stuff than we're going to get to. So far, there's no actual physics. It's just sort of some kind of formalism. And so this is going to be kind of secretly, you should think that that this is sort of the theory T sub A for a CDO on Y. So this is some kind of, so there's maybe a few flavors of chiral algebras, commutative ones, Lie star ones, and then these funny CDO ones, which are some versions of differential operators. It stands for chiral differential operators. And its category of modules is some maybe twisted version of D modules on the space. And like, let's not get into those twists, but basically, if you want to try to think out like what are the structures here and things like that, you can use this as kind of an analogy a little bit. So you can sort of think like, what should be the chiral homology functor in this way? What should be the unit object? And you'll get all of the answers just basically from example 1 and sort of allowing yourself to maybe be non-affine or stacky or whatever. So this is kind of like if y is like smooth and affine. Okay, and then there's one other kind of example I want to say. So like with y as before, then there should be a theory. And here this gets like a little bit wonkier, so maybe for subtle reasons that I'll just ignore. There is a 3D theory attaching the category of what are called incoherent sheaves on the space of maps from the punctured disk de Rham to Y to this sort of punctured disk at a point. So this is some category. So let me just say, INCO, I'm writing it here, but it's ambivalent. So it's not necessarily defined in this level of generality, and there are kind of big subtleties that come up along the way here. And so take this a little bit as a metaphor if you happen to know what those words mean. If you don't know what those words mean, you can think like quasi-coherent sheaves, except that I'm like being ambivalent about certain kind of difficult subtleties with homological algebra for difficult rings. And one of the, I should say, like major problems that Justin and I faced in our work was really kind of making sense of this in our example of interest. Just as kind of an example for what this kind of thing means. So if y is equal to something like the classifying stack for a group, then this maps from the punctured disk de Rham into y is equal to the space of like G local systems in the de Rham sense. So what I'd call locus G on the punctured disk, which equals kind of de Rham local systems on the punctured disk. What does de Rham local systems mean? Let me answer out loud. So again, I'm working in algebraic geometry. So normally, if you think about local systems on a circle, it's not maybe so interesting. So it's basically, it's a conjugacy class inside of this target group G. And just because the fundamental group of the circle is not super interesting. But in geometric Langlands contexts, it's helpful to remember that that's not true, that actually there's a kind of robust alternative theory of local systems, which is the theory of basically algebraic differential equations with Laurent series coefficients. And so those can have irregular singularities and so on. And when you consider them up to algebraic equivalents, as opposed to kind of analytic equivalents or topological equivalents, that becomes a much less trivial theory. It's something much bigger and more robust. And that's the kind of thing I mean when I say de Rham local systems on the punctured disk. So I only allow algebraic changes of coordinates. So for instance, the differential equation for like e to the 1 over t or something like that is something you can solve holomorphically, but you can't solve it with a Laurent series. And so that gives you a non-trivial local system on the punctured disk, even though its monodromy is, so to say, trivial. And so there will be sort of another example that I'll care about. Maybe I'll just write if y is A1 mod GM, which will be an example of interest for us, then this maps from the punctured disk de Rham into y is equal to the moduli of a line bundle with connection, so L nabla on this punctured disk, plus the data of a flat section. So you'll write gamma, say gamma nabla with L. So oops, a flat section. So just kind of geometrically, like a line bundle with connection admits a flat section if and only if it's trivial, a non-zero flat section. And so you can kind of imagine that it's like you have some kind of moduli space of local systems, and then you have this sort of line sticking out over the trivial local system that is kind of parameterizing those sections over it. And I mean, eventually I'll try to explain a little bit more what's happening in a later talk, but that's the picture to have. How that line is attached is a big deal, but not at first pass. And so this is sort of secretly the 3D theory for the chiral algebra A, the kind of the constant chiral algebra, constant commutative chiral algebra with fiber equal to functions on Y. Again, this is Y affine. Okay, so so now I told you what. Okay, do I have until? I forget how long the talk is. Is it 50 minutes or is it an hour?
I think you have an hour.
Okay, great. So at this point, I told you what a 3D theory is, and I told you like a sort of algebrogeometric means for constructing them. So so you get them for chiral algebras, and you get them, okay, maybe in sort of non-affine versions of that theory, the way like you know, like sort of some kind of maybe more global or stacky objects, that kind of thing. And there are certain particular examples that will be of main interest for us. There's another sort of a little bit, let me say, slightly vague way of producing these things. So, so another kind of way these often appear, algebraic theories appear, is via kind of, say like holomorphic, topological, so holomorphic in two directions and topological in one direction, twists of, you know, what you could call it kind of like analytic, you know, like just sort of like normal, that's all I really mean, quantum field theories. So normally, like if you're a physicist, you write down, you know, again, basically some kind of system of differential equations that you try to quantize. It's like Euler-Lagrange system for your Lagrangian. And that's something that occurs like really in the world of like manifolds and differential geometry. That is its nature. There's not some field of characteristic zero around. There's like R and C, and like they're not there's not a lot of room for that. And so but it happens that sometimes you start with these theories. So so maybe kind of general background here is that, which I'm going to just say sort of in not a ton of detail, but just enough for like myself 2 years ago listening to this to be able to black box things. So so supersymmetric theories, QFTs, have twists. So these are like sort of other kind of in some sense deformed quantum field theories. And like again, if you think about quantum field theory as something like an associative algebra, you can deform one associative algebra to another, and that's the kind of thing you do with a supersymmetric twist. And like in practice, deforming an associative algebra, it looks like it should probably be a DG algebra, and you maybe want to add a term to the differential that satisfies some Maurer-Cartan equation. And that's the kind of thing that supersymmetry gives people. If you've those words mean anything to you. And these are sort of like often in practice, these are kind of, let me say like nicer. So like maybe holomorphic or topological. And then there's this thing that in practice, again, if you're not too crazy about things, these in particular holomorphic in two directions and topological in one direction twists are producing for you these algebraic theories. So so let me say kind of more specifically. So if you have a 3D n equals 4, so whenever theory, so let me just sort of make an aside visually here. So if you have an n equals 4 theory, so this is kind of how much supersymmetry you have. Just if you haven't looked at this stuff before. So that's basically telling you some measure of like, what are the possible ways to twist? What are the things you could add to the differential to get a new deformed algebra? And let me just say that whenever I say something like 3D n equals 4, I'm thinking like analytic setting. So I'm talking about like usual quantum field theory, differential equations, and not the algebraic stuff I was talking about earlier. So I want to talk about the setting of 3D n equals 4 theories, which is where mirror symmetry occurs. So if you have a 3D n equals 4 theory, so theories like T, let's say, have two, in fact, just purely topological twists that I'm going to call T sub A and T sub B. And like often these are algebraic. Or when I say it is algebraic, I mean there's some algebraic cousin for it or something. So I want to just give some like kind of formalism for how we manipulate these theories. And so I'm going to just kind of imagine that a 3D n equals 4 theory always gives me these algebraic things, even though I should put more words on it. It's kind of, and then sort of moreover, a 3D n equals 4 theory T has what I'm going to call an abstract mirror dual T star that is the same theory, but the supersymmetry like algebra is conjugated by automorphism. So and let me just say the basic property is going to be that like if I take the A twist of this dual theory, so this is going to equal the B theory, the B twist, and the B twist of this theory is equal to the A twist of the original theory. So that's what this abstract mirror dual does. It's like an extremely innocuous construction. And this is some, I sort of don't want to talk about supersymmetry algebras like in any detail. So just maybe believe me that this is kind of the way things work. There are these two topological twists, and there's this way of just like changing the embedding of the supersymmetry algebra so that like what you used to call the A twist, you now call the B twist. So where do these 3D n equals 4 theories come from? So the answer is basically sigma models with symplectic, or so kind of sort of say like algebraic. I'm just going to emphasize symplectic targets, sort of like AKA in the physics literature, hyperkähler targets. So to sort of simplify quantization issues, I'm going to assume that my targets are T star Y, or sometimes it's helpful to think in terms of twisted cotangent bundles also, and it doesn't really matter so much. So for some maybe smooth Y. So, okay, so Tom's asking, are these statements big theorems, conjectures, or tautologies? So right now, this is a tautology. So all I'm saying is you have one theory, you can change the way the supersymmetry algebra is embedded. And that's why I say it's a sort of abstract mirror dual. It's just like kind of, it's like you just take the thing you had and you just relabel things. That's all I'm trying to say. So I'm going to say, so let's let T sub Y be the sigma model with target T star, sorry, T star of Y. I see that the T's are bad, but I hope it's not too terrible. So yeah. So maybe I'll just mention very briefly. So at some point, we want to talk about these quantum field theories, and what we'll see is that only the twists make sense algebraically, and so maybe people will object a little bit that that there should be something better out there. But in fact, as far as I understand, the actual 3D n equals 4 theories here are non-renormalizable, and they only become like good theories after you do the twists. There's something a little bit funny, which is like this sort of posits that the quantum theories make sense, but in fact, the quantum theories kind of don't make sense until you kind of, in some sense, break the symmetry by passing to A twists or B twists. A little mysterious to me. Yeah, so I see that I'm out of time, so maybe let me just sort of briefly say, so what these theories do on the punctured disk, what these I should say, what the theory attaches to a circle is called the category of line operators. So I can take this theory attached to Y, and I can take this A twist, and I can take this punctured disk, and this is example 2 we talked about earlier. So this is the category of D modules on the algebraic loops into Y. And I can also take this B twist, and this is going to be example 3 that we talked about before, which is indco on this space of maps from the punctured disk to RAM into Y. Just sort of, let's just say very briefly, 3D mirror symmetry, which is, you know, a flavor of conjecture. So it makes assertions like the following. So you have some, I'm going to change into this notation X. You have X and X star, two stacks that are said to be 3D mirror dual. They're examples. So I'm not just saying this is like some abstract thing. There are examples out there, and where the examples come from is a different question. And then this is such that the theory for X, A twisted, is equal to the abstract mirror dual of the theory. Sorry, I should just say this, is equal to the abstract mirror dual for this for this mirror dual stack. So if you have, so for instance, this predicts if you sort of pass to A twists, that the category of D modules on loops into X is equivalent to the category of incoherent sheaves in the space of maps from the punctured disk to ROM into this X star. Yes, that's so Matt is okay. Oh, everyone's okay. I see. I missed a couple comments. So first of all, for Tom's question, so this is the kind of thing that's like a big conjecture or a big theorem. I mean, whatever. This is the kind of stuff that like is like non-obvious, so to say, not a tautology. Is an assertion like this, and the upshot of these talks will be that we have an example where we can really prove this kind of thing. Yes, okay, and then Matt's saying that isn't assuming that the target is a cotangent bundle very restrictive. The answer is absolutely yes. In many examples, mirror dual pairs are, for example, twisted cotangent bundles. Even if you start with something like well, okay, even if you only kind of start with cotangent bundles, you can get twisted cotangent bundles in this way. I'm eliding this issue out of sloppiness. So basically, there's a couple things around. One is that there are issues in quantizing theories if they're not cotangent bundles. There are issues already on the B side if it's just a twisted cotangent bundle. And so this is just like to write down these formulas, I'm assuming that I have this, that it is a cotangent bundle theory. The second thing is like, my examples are cotangent bundles, and so I can get away with this. And the sort of last thing there is like, there are, maybe that was it. Yes, so if I had a linear, so what Justin's saying is correct. So if I had a linear target and it was like not gauged, then I'm assuming it's of the form V times V dual for some vector space V. So it's not the same as saying that I have a UV Lagrangian. Again, I have the sigma model with some hyperkähler target, and I'm assuming that my hyperkähler target is the cotangent bundle of some stack or variety or whatever. And I'm kind of, so it breaks the symmetry, but that symmetry kind of, it gets broken when you quantize. It's like a subtle issue. Sometimes it does get broken, sometimes it doesn't get broken. There are kind of metaplectic corrections, things like this that occur. There are issues on the thing. What? Why not? Oh, wait, is that the, Matt, I see your comment that you wouldn't call that a sigma model to, yes, it's a gauged linear sigma model, yes. That's what normal people would say, but it's also.
Sorry, why is the gauge group abelian? It's just a gauge sigma model.
No, it doesn't have to be abelian. In our theorem, it'll be abelian eventually.
Sorry, that is a nomenclatural question.
But where's the word abelian? Yeah, so what Justin's saying is right, which is like the gauged linear sigma model, like at the mathematical level, it behaves exactly the same as a sigma model with target the cotangent bundle of the stack. And so I'm just going to, even if it's unpopular, say it that way. Like for me, I mean, gauge theory is a sigma model with targets and stack. In fact, it's a global quotient. I know it's not what everyone feels in their heart, but Um, the target of the sigma model physically will involve. So wait, first of all, my talk's kind of over and we're like in the question period now, right? Am I reading the room
Yes, this is
correctly?
the question period, I
And
assume.
maybe we should all clap
Yeah.
first. Thanks, Sam.
I didn't know it, but that's what I was missing in my my ear. Okay, so it will involve a stability condition for the quotient. Why? So
Maybe now that we're in the question period, we can unmute the question askers and they can speak.
Hey Sam, thanks for the talk. I think it's just a question of semantics, perhaps, but you know, normally, like physically, there's a D-term equation, and when
wait, a what equation?
A D-term equation, which is translated into stability condition. So you know, like even in your examples, right, when you have a global quotient, like physically, the target space of the sigma model will not be a cotangent model. Like, for example, it will be an Nakajima quiver variety. Like even if the matter representation is a cotangent bundle, physically the quotient will not be, because there's, you know, physically there's always a D-term equation that you have to solve.
So maybe, okay, I don't know this phrase D-term, and maybe Justin can chime in. But what I'm guessing is that that's about, is it like flatness of the moment map? Is it related to that?
No.
I think Matt, I think he's setting all of the masses and Fi parameters equal to 0. And so that's hence the stackiness.
Won't there still be a stability condition? Even there'll still be a D-term equation, even if you set the Fi parameter to 0.
Oh yeah, absolutely. But I mean, the quotient is very stacky. It's not pretty far from being smooth when you set all of the Fi parameters and masses to 0.
Yeah.
Like,
So
for
Matt,
example, if I take like super, you know, if I take like the mirror of super QED, like the Hicks branch at 0 Fi is the closure of the nilpotent cone.
no, but Matt, we have like a long running
That's a cotangent.
discussion, right? Like between you, Tutor, and like myself about like whether 0 Fi parameter should be the just the affine quotient, or whether like you should just take a stack quotient. In which case, like you would have like a quiver stack whose like affinization is the nilpotent cone. Like,
Yeah.
I mean, I don't know that this is like a question that could be answered physically. It's just like it's a purely I think all we can agree to do is agree to like what specifically what terminology we're going to use.
I think it might be okay if
And
your 3D theory, if you think of your 3D theory as the boundary of a 4D theory, because there I think you don't have to, I mean, with a Neumann bound, I don't think you have to impose the D-term equation when you do that. But if it's
So
a 3D theory, I think probably you do.
So I can say in our example, there's something that's like literally true, you know, that fits into this sort of framework of conjectures. You're welcome to think, I mean, sort of because we work abelianly, it's like not such a big deal to think of it as a boundary for a 4D theory, or to forget the 4D theory. If you forget the 4D theory, then one side looks like the B twisted side looks like, you know, SQED, like you say, it's like some with one hypermultiplet. It's like so for me, the target is the cotangent bundle of A1 mod GM. So like any sort of GIT sort of theory for that is going to produce something totally trivial. But like
yeah.
for our theory, you know, like we have this equivalence of categories that are defined in terms of the stacks, and that sort of essentially, kind of tautologically, if you do this in terms of the stacks, you'll recover the BFN construction of Coulomb branches and the I don't really know who to attribute it to, the sort of normal construction of Higgs branch on the other side. So it's sort of is compatible with those kinds of standard constructions. It's like some I would say like big refinement of those sorts of comparisons.
But Matt, I agree with you that like physically, like precisely like what you want to say in order to get the stack out as your answer isn't completely clear about like why you could ignore the D term when you set the FIs to 0.
I think it might be okay if you're at the boundary of if you think of like gauging as coupling to a 4D gauge theory.
Yeah, but this is just like the ansatz that like that I've sort of found gives like the right answers when I plug it in. Like I agree that there's something physically fishy, but like mathematically, I'm sure it does something reasonable.
Yeah, but like in the physics, I mean, you also like if you think about them as at the boundary of this U1 gauge theory in our example, like in that case, Dirichlet is like S dual to Neumann, and so you do get this like 3D sort of mirror dual pair. I mean, we'll talk about 4D mirror duality next time, but like you do get this like sort of 3D mirror dual pair, and so it's sort of allowed to like think of it at the boundary of a gauge theory or not, and so anything sort of must explain. I think that there should be some. If you think that considering it at the boundary solves the problem, which sounds reasonable to me, then there must also exist a physical explanation for why you can forget the boundary. So, or maybe the bulk theory, maybe is the way to say it.
I think Chris has a question.
Yeah, thanks. That was a great talk, by the way. I really enjoyed it. I had a question just about these algebraic 3D theories, this language. You explain what they assign in sort of dimensions 1 and 2. Does it ever make sense to extend them up to dimension 3? You could imagine, for example, I don't know, like the formal punctured neighborhood of the 0 section of some vector bundle on a curve, and you can imagine some kind of language like this that's assigned maybe a number to such a thing.
So I kind of didn't. I'll say I like sort of didn't think seriously about it, but I think that what you would, so yeah, I think that it probably should be kind of doable. Like you could imagine having like a curve crossed with like an arbitrary manifold as your input, and like think about what sort of functoriality you get from that. I didn't do it, but I mean, like in 3D specifically, it's probably not possible to do very much that's going to be more interesting. Like you could extend to a circle or something, but we'll talk next time about 4D or whatever. It can kind of go into higher dimensions with the same ideas, and I think that probably it should be fine.
Thanks.
Yeah, and yeah, I would. In some ways, you're like a more resident expert on that than me.
We have another question. Go ahead.
Hi, thanks for the great talk. So my question is, I just wanted to understand, make sure I understood your construction of this 3D theory from the chiral algebra correctly. So if I understand you right, you can do like a topological version of this where X is just a topological surface, is that right? And then you would just have an E2 algebra, and what you'd be doing is taking the topological chiral homology of the E2 algebra and associating that to the surface.
Yes.
And then the category you associate will not depend on the point anymore, and that would just be modules over this E2 algebra.
Correct.
It is now an E1 monoidal category, and is that what you associate to a point in this 3D theory?
That's in fact, it's I consider the E2 modules over this
E2 module, yeah, which is now an E1. That's
it's actually an E2 category.
You're looking at modules over the E2 algebra.
So I mean, there's different notions of modules. Like if I were talking about E1 algebras, I'd be talking about bimodules for the algebra.
Right.
So you sort of are coming in from both sides of R. And in the E2 picture, I'm talking about modules where you can sort of come in from all directions.
Right.
So E2 modules, it's like bimodules form a monoidal category, and E2 modules or EN modules form an EN category. So as opposed to like left modules over the guide, that's something that doesn't really have an analog in the VOA world.
But the thing you want to associate to a point is an infinity 2 category, right? A 2 DG category, whatever.
Yeah, it's like DG categories that have a map from like that E2 algebra to their Hochschild cohomology, to their center.
Oh, I see. To the E2 Hochschild homology, or sorry, I'm getting
Well,
right.
So what people usually call the Hochschild cohomology of the category is naturally an E2 algebra, and I want a morphism of E2 algebras. So it sort of means like I have this E2 algebra A around, and I want HOMs in my category to be like A modules in a functorial way.
Right, I see. And so coming back to the holomorphic situation, the one that you're in, I should be able to recover some three-dimensional factorization algebra from the structure you described, right? Which is this co-sheaf of DG categories on the round space or something.
Maybe I wouldn't say it's a 3D. I mean, there is some factorization category around on the round space. I agree.
Of X, but then there's a three-dimensional thing, right? There's a three-dimensional theory which should have its observables should form a 3D factorization algebra.
No, it's the same issue I was saying about like the dimensions get confusing. So like it's like if you start with observables for like a 1D quantum field theory, just to make things more simple, like those observables are like a factorization algebra on a one manifold like R, and but also if you consider them sort of say like up to Morita equivalents, like you consider just the category of A modules, that's a 2D TFT, like that controls that category and attaches that category to a point. And the sort of relationship with usual quantum mechanics is you have this Hilbert space that's like some preferred boundary for that 2D theory. So the annoyance is like, you know, there's like different ways of formalizing ideas of quantum field theory, and they get a little bit, you know, jumbled together. But like, if you're starting with the functorial perspective, like if I talk about functorial QFT as like the Atiyah-Siegel kind of framework, then like starting with then sort of like deformation quantization produces an n+1 dimensional functorial theory, whereas like geometric quantization produces an n-dimensional theory. So and at its boundary. And so that's what's happening here. Is we're just we have this algebra of local operators that look like a two-dimensional conformal thing, and then we're producing some three-dimensional, partially like topological in that direction and conformal in the two directions thing. That's the sort of, I don't know. Ben Zvi, who says he learned it from his student Pavel Safronov, told me that the n+1 dimensional guy should be called the theory of observables, and the n-dimensional theory should be called the theory of states. I'm not sure this is widely used terminology, but it's a helpful distinction, I think, to keep in mind for this stuff.
Are there any other questions? All right, if not, let's all thank Sam again.
Thank you.